So we find ourselves in the age of agents. Now that LLMs have reached a certain level of general capability in so many tasks, everyone seems to be racing to assemble groups of LLMs into agents that can solve more and more complex problems across greater and greater scales, and actually try to deploy these things in industry across, hundreds, thousands, millions of users and hundreds, thousands, but perhaps millions of distinct tasks. So how do we actually do it well? How do we know whether we're getting anything close to optimal when we're trying to orchestrate these agents together into larger and larger systems? So that a standard approach so far has just been to say, look, LLMs, they're kind of like humans. They kind of feel like humans to interact with. Maybe we'll think of assign each one a role, like we would assign a human a role in an organization and at that level. But can ask, is that really optimal? Is the same organizational structure used for humans going to be the optimal one for machines? And our position in this paper is no. The optimal organization for machines is going to be a machine-like organization, not a human-like organization. And to show that, we advocate for using asymptotic analysis, this core methodology from the origins of computer science, um, for reasoning about how processes behave and how efficient they are at scale. So we hope that by using this analysis, one of the key implications is that one, we clearly shouldn't just have a giant, big AI that does everything, including the smallest, dusting up some dust in the corner. And we also shouldn't have AI organizations that look exactly like human ones. But in the limit, what this is pointing towards is many, many, many multiples, millions of tiny agents with perhaps larger and larger ones orchestrating them in a manner that looks more like an ecology with maybe a few big agents on top, hundreds, thousands of medium-sized agents, and then millions, billions, trillions of tiny ones at the bottom. So the core concepts we define in the paper are notion of language-based algorithms. So encapsulating every LLM call as this LLM primitive that we count in our analysis. And then these are chained together into language-based algorithms. And it's important also to assign LLMs, enumerate exactly what their capabilities are. So we know we can do simpler things with smaller ones, more complex things with bigger ones. And it's useful also to have a notion of this oracle decomposition. So given a particular problem, what's the best possible way we could decompose it in a way that we can then algorithmically recombine the parts to solve problems. In the paper, we give some examples of how this could be a powerful methodology for analyzing systems. We cover some task routing, which is increasingly common in industry, code debugging, which LLMs are being used for coding all the time, and in optimization, where LLMs are increasingly being used for optimization in general. And our analysis shows that many of the approaches so far are potentially suffering from exponential or super exponential inefficiencies due to some kind of basic algorithmic assumptions that they're missing out on. These are really just a taste of what can be done. There's tons more to be done in making this framework actually, practical and cover everything we care about in building multi-agent LLM-based systems, handling stochasticity and asynchrony and automatic problem decomposition and online learning. And please go to the paper for many more interesting areas of future work. But mainly, we just want to show we think this is really the right way to look at these systems and to try to understand them. And this is also an invitation for algorithmists who maybe didn't see an obvious place for themselves in the cutting edge of AI, but we really need you to look at these systems and try to understand how they should be built so that they can be, more environmentally friendly, but also scale to more and more complex problems in science and organization and optimization and things we really need to solve. But it's also just something that we really want anyone building LLM-based multi-agent systems to keep in mind. There may be these underlying inefficiencies that you don't have to just accept that things are going to be very costly and justify more and more compute. There may be these opportunities to get huge asymptotic improvements, especially when your deployments become really large. So um, that's all for the high level overview. Please check out the paper, which has a bunch more details, some fun exercises for the more algorithmically inclined, other interesting implications for other areas of AI more. So enjoy.